Hello. In this video, I'd like to talk about the random variable and how we use the random variable to create a probability distribution. A random variable is a variable now that takes a single numerical value, and that value comes from some chance process that represents the outcome for that chance process. An example of this would be flipping a coin, or rolling a die, or selecting a card from a deck of cards. Now, these outcomes, for like rolling a die, are numeric by nature. 1, 2, 3, 4, 5, or 6. But if you talk about flipping a coin, the outcomes are heads or tails. Those are non-numeric. They're nominal level data. So if we wanted to use a random variable to represent its outcome, we would have to assign some numeric value to heads or tails, like arbitrarily just 0 or 1. Or we could use something else, which we'll discuss later. The same thing for a deck of cards. If you select a card from a deck of cards, sure, there are cards numbered 0 through 10, but they're different suits. We have the face cards, we have the ace. How do we assign some numerical value to those cards? And we'll get into that as well. But first, once we've identified the numerical outcomes for our random variable, we can create a probability distribution, which is a table now where we list out all the possible numerical outcomes and next to them their associated probabilities. Let's look at this example for rolling a six-sided die. X is going to be our random variable whose values are the outcomes from rolling a die. X is a random variable because the outcomes are chance outcomes. But since the outcomes are all equally likely, given you have a fair-sided die, then we can use classical probabilities to calculate the associated probabilities for each of the numerical outcomes. Here's the probability distribution from rolling a six-sided die. You could have the outcomes of 1, 2, 3, 4, 5, or 6, and because they're all equally likely, their associated probabilities are 1/6 for each possibility, for each outcome. But now, this is the easy one. Let's go to something a little bit more difficult. Suppose we have a deck of cards now, and I'm going to create like a table game, or maybe like a slot machine, where we have 3 wheels, or we're going to select 3 cards, and if you get 3 aces, then you're going to win $1,000. Or if you get 3 of a kind, in other words, you get 3 of the same suit, you're going to win $100. Or maybe you just get 3 of the same color, I'm going to give you $10. If we're just talking about selecting cards one at a time, then I'm going to select them truly one at a time at random and with replacement. So if you wanted to extend this to maybe like a slot machine, you could say we have 3 wheels on a slot machine. Each wheel has all 52 cards from a deck of cards, and they're going to stop at one of each card. Each wheel will stop at one of each of the pictures representing each of the cards. And so if you get 3 aces, you win $1,000. If you win 3 of a kind, you win $100. And if you get 3 of the same color, you win $10. Now, remember, a random variable is a single numerical value. So we can't say that the outcomes from a random variable are 3 of a kind, or 3 aces, or 3 of the same color, or all the other non-winning hands, because those aren't single numerical values. So what we're going to do is we're going to let our random variable represent the amount of money you can win from playing this game. For example, in this case, then our outcomes would be you could win $1,000, you could win $100, or $10, or you could win $0, which represents the numerical monetary amount awarded for not winning. So in order to find the associated probabilities for each of these outcomes so that we can create a probability distribution, we need to do exactly that. We need to find the probabilities of each possible outcome. So first, what's the probability of getting 3 aces when you select 3 cards at random and with replacement? Well, using the multiplication rule, Oops, I need to go back. Right? So now, using the multiplication rule, we have 3 cards we're going to choose. We have our first card, second card, and third card. And what I need to figure out is, what's the probability of getting an ace on the first card? And since there are 4 aces and 52 total cards, yeah, the probability is going to be 4 over 52. Or if you wanted to simplify that to ease your calculations, yes, that's going to be 1/13. Now, since we're drawing the cards with replacement, then the probability of getting an ace on the second card will be 4, because there's still 4 aces out of still 52 cards, or 1/13. And the same for the third card, 4 out of 52, or 1/13. And by the multiplication principle then, the probability of getting an ace on the first card, an ace on the second card, and an ace on the third card is just to multiply those probabilities. This gives me a probability of, now if you don't simplify it, you're going to get 64 out of 140,608. The reason why I didn't simplify these is because these numbers are actually quite meaningful. There are 64 ways we could get 3 aces by selecting 3 cards at random with replacement. And the bottom number represents the total number of ways that you can get any outcome. The total number of possible outcomes from this process is 140,608. This gives us an approximate probability of, as a decimal now, 0.000455. And that's rounded now to 3 significant digits, or in this case, 6 digits to the right of the decimal point. Now, let's continue. Let's find the associated probability for getting 3 of the same suit, or the probability of getting $100. Now, if you use the multiplication rule, this is a little bit tougher to figure out because of the first card. If you do something similar to what we did in an earlier video, then it's not so bad. But consider this. We have 3 cards. You got the first card chosen, the second card chosen, and the third card chosen. Now, if we want 3 of a kind, 3 hearts, 3 diamonds, 3 spades, or 3 clubs, the first card is going to basically determine the suit that we want 3 of a kind on. So really, for the first card, we're looking for the probability now of a suit. And you're like, so I want to know, what's the probability of getting a heart, or a diamond, or a spade, or a club? Well, you're guaranteed of getting one of those, because you have to get one of the suits. In other words, the probability of getting a suit, a heart, or a diamond, or a spade, or a club, is 100% for the first card. Just one. You're guaranteed that's going to occur. But now, we get one of the 4 suits from the first card. Now, we want to know, what's the likelihood of getting a card of the same suit on the second card? Well, now, you're locked into one of the suits. There are 13 of the same suit still left in the card, because we're doing it with replacement, out of 52 total cards still remaining. Or you could simplify that to 1/4. The same thing for the third card. We are now locked into a suit. There are 13 cards of the same suit remaining out of 52 total cards left. And the total number of ways of getting a suit on the first card, the same suit on the second card, and the same suit on the third card is just the multiplication rule. This gives me a calculated probability, if you simplify everything now to 1 times 1/4 times 1/4, well, that's 1/16, which is equal to, as a decimal now, 0.0625, 6.25%. Let's move on to the next possibility. How about the probability of getting 3 of the same color, which is going to be the probability of getting awarded $10 now? Here we have our 3 cards, and we're going to calculate the probability much like what we did for getting 3 of the same suit. Here's our first card, second card, and third card. By the time we draw our first card, we haven't established what suit yet. So really, the probability we're looking for the first card is the probability of getting a red or a black card, which is 100%. You are guaranteed to get a red or a black card on your first card. But now, once you've selected your first card, it's going to be red or it's going to be black. But now you're locked. For the second card has to be the same color, and there will be 26 of the same color in the deck, because we're doing it with replacement, out of 52 total cards. And then for the third card, it's similar. You are going to have 26 of the same color for the first and second card out of 52 remaining. Then using the multiplication principle, 26 out of 52, that's the same thing as 1/2. So 1 times 1/2 times 1/2 gives me 1/4. Or as a decimal, what? 0.25. A 25% chance of getting 3 cards of the same color. Now, the last one, which is the probability of a non-winner, or winning $0 now for your random variable x. This one seems like it might be a little tough because you have to think about what are all the ways I'm going to lose or not win any money. Well, what's going to be easier to calculate is the probability of winning any money, which is the probability of winning $1,000 or $100 or 10, which we've already calculated. So really, if I want to calculate the probability of $0 or not winning any money, I'm going to use the complement rule and just say, all right, well, let's subtract the probability of Charlie Sheen, which is winning, from 1. That's the complement of not winning any money. So I take 1 minus the probability of winning, which is really going to be the sum of the probabilities of winning any money, because they're all disjoint. You can't win $1,000 and at the same time 100, or for that matter 100 and at the same time 10. You have to win one or the other. So 1 minus that 0.000455 plus 0.0625 plus 0.25. I'm going to add up the probabilities of winning and subtract that total now, which is why I put them in parentheses, from 1. So this is going to be 1 minus a 0.312955. So the probability of winning will be about 31.2955%. Therefore, the probability of not winning then is going to be 0.687045. Let me fix that. That looks a little sloppy there. 0.685045. And the way that we calculated that was just using the complement rule for probability. Now, we're going to conclude this by filling out the probability distribution. We know the probability of winning $1,000 is 0.000455. The probability of winning $100 is 0.0625. The probability of winning $10 is 25% or 0.25. And finally, the probability of winning nothing is 0.687. 045. And that is your probability distribution from our game. And one of the reasons why we do this is if you look at this distribution, it looks sort of like a relative frequency distribution. And truly it is, except we don't have our classes now are really the award amounts. So one of the things we could do is we could calculate the weighted mean. Each outcome times its associated mean, which would be the probabilities. And another name for that is what we call the expected value, which is something we'll talk about a little bit later in this chapter. But the expected value for our random variable x is just going to be found by taking the sum of the products of each outcome times its associated probability. So if I were to multiply each outcome times its associated probability and add them up, what I would find is this, that on average, my game is going to award